Hello, everyone. I want to say thank you in advance for joining me today. I'm glad to have you in this session on emergency power supply as used in 800-volt bus for electric vehicle application. So my name is Edward Ong, and I work as a senior product marketing manager for Power Integrations. I manage the product line for automotive, mid-power, and energy saving devices. Okay, so for today, I'd just like to give you a background what we're gonna sort of discuss. So I'm gonna start with giving some context background about 800 volt bus for electric vehicle. What are the trends driving it, and some other key topics that are affecting or influencing the requirement for emergency power supplies. Okay, so for this slide, we show the different block diagrams inside an electric vehicle. So we have, of course, the traction inverter, the DC-DC converter, battery management systems, onboard chargers, climate control, and so on. For our discussions on emergency power supply, the one that will be of interest to us is this orange block here, which is a traction inverter. So the traction inverter gets its input from the high voltage bus, and then it has, IGBT or silicon carbide module drivers driving a motor here. And then the motor is the one that causes the vehicle to propel. And so this is where we're going to be focused our discussion, because this is where the emergency power supply is going to be used. Now, just think of it, the traction inverter is the one that replaces the traditional internal combustion engine of a car. So it used to be purely mechanical here, and now it's being converted into an electrical through this traction inverter system. Now, in terms of the bus voltage, we're going to talk about, the different bus voltage that are currently used in electric vehicle. So the passenger vehicle are, consumer vehicle type of cars currently are predominantly using what we refer to as the 400 volt bus. So this is DC, coming from the lithium ion battery pack, and it generates the 400 volt bus that is then distributed throughout the different systems in the vehicle as shown in the earlier slide. Now, what's interesting is that there's a higher bus voltage that are currently also used, which is double this. It says 800 volt bus, and it is currently used in what we refer to as commercial vehicles. So what I mean by commercial vehicles are, trucks, buses, tractors. They all use 800 volt bus because they, require much more power for their traction inverters and so on. So they need to operate at a higher bus voltage. And also there are some high performance vehicle like this shown in the picture here, the Porsche Taycan that was announced September of last year. These are high performance consumer vehicle that again uses 800 volt bus. Now, what are the advantages of 800 volt bus besides providing more power for your traction inverters, allowing you to be able to accelerate faster and so on? So besides that, the other advantages of adopting the 800 volt bus is that it enables a faster charging. And so you could reduce significantly the charging time by migrating to a higher bus voltage. So you could come up, for example, be able to charge for a range of 100 miles in just about 10 minutes or less. Okay, so that's one of the advantage or reason for migrating towards the 800 volt bus. So in general, The 800-volt bus, because power is voltage times the current, and if you are distributing a higher bus voltage, in this case twice the usual 400-volt bus, so you are able to get either the same amount of power with lesser current, and so the I squared R losses are much significantly reduced. And because the I squared R losses is on the second power, so cutting the current by half actually reduces I squared R heating losses or power losses by 1/4. Okay, and so of course a thinner wire due to a smaller current allows you lighter and lesser weight as well. So there's a lot of neat advantages going to 800-volt bus, and that's why that is we see are the migration for the future of electric vehicles towards higher bus voltage. And we'll talk more about that in the coming slides, okay? Of course, migrating towards a higher bus voltage also generates a different kind of challenges for the designers. So, of course, one of this is that, the main powertrain is there's a growing popularity in adapting towards silicon carbides, which are, performs much better as you go towards higher voltage. And as shown in the picture here is a gate driver that is driving a 1.2 kV silicon carbide module. So, the trend towards higher bus voltage is pretty allows a facilitation of migration even further towards adaptation of silicon carbide technology in terms of the power switches. And the other challenges, okay, and so there are sort of different challenges as we use or migrate from IGBTs to silicon carbide that we need to take into consideration. Such thing as a quick response to overload or short circuit condition and so on. So there are specific design considerations that have to be addressed as we migrate towards a silicon carbide design. The second thing, the challenges is that because now you need to operate at a much wider input voltage range. And I'll discuss this in more detail. So it generates, the challenge we're in, especially in automotive, where in opto-isolators are not recommended due to reliability concern. And so it is much sort of a challenge. How do we regulate, the output voltage of power supply systems if the bus voltage could be varying a very wide input voltage range? It's something that we'll see how we are able to mitigate that. Okay, of course, efficiency and its related thermals are going to be a challenge for us because we know that the switching losses varies by the square of the bus voltage. So if we would double the bus voltage for the same, say, switching frequency, then you basically, quadruple the switching losses. And so, high efficiency design becomes even more and more important as we migrate towards higher bus voltage. And again, we're going to talk more about that in the coming slides. Now, is it 800 volts, nominal is going to be, what it is going to be in the future? We're actually seeing more and more companies are looking at even higher than 800 volt bus voltage. And so we've heard some companies already adopting in their new designs 900 volt bus. And again, it allows, lesser or lower generation of I squared R losses, which translates into heat, and so we've also been working and discussing with automakers wherein they're looking at, stepping it up to 1.2 kV in the future. And so there is then the need to be able to come up with a design wherein you can readily scale up your design, your power supply design, in order to be able to meet even future higher bus voltage, okay, without still being able to reuse your current design. So a scalable design technique is very much useful for this case, which is going to be one of the main topic we're going to be showing. Now, the other topic that is gaining a lot of significance right now is what we refer to as ISO 26262. And what ISO 26262 pretty much says is that in the event of a fault condition, the vehicle should always be safe to operate by the consumer or by the user. And so the ISO 26262 requires some changes or some adaptation of perhaps some form of redundancy to be able to address such functional safety requirement. And so this is the reason ISO 26262 is the one that is mainly driving the need to add what we refer to as an emergency power supply. So an emergency power supply, we'll discuss in more detail what it is, but it is pretty much what we refer to also as a backup or safety power supply, okay? And it is usually placed together with the gate driver boards, and again, they are all used inside this, what we refer to as the traction inverter block. Now, how does an emergency power supply work? And you could see on the schematic diagram on the right of the slides is that the 12-volt battery, yes, electric vehicles still use the conventional 12-volt battery. It is used to power up the gate driver voltage, provide the gate drive voltage for either an IGBT module, for the gate driving of the IGBT module, or a silicon carbide module. And so the concern or the fault, for example, will be in the event that the 12-volt battery gets discharged below the acceptable level of voltage, or if the 12-volt battery fails or the 12-volt battery gets disconnected, then you basically lost the gate drive voltage for your traction inverter, and it puts the switches, the IGBT modules or silicon carbide module in an undefined state. And so that is, poses a risk to the user because the user is not able to properly control the vehicle in the event, safely operate the vehicle in the event that the 12-volt battery goes away. And so as you can see here in the schematic, we've added the emergency power supply here, and it is operating at a very wide input voltage. So just imagine that the output of the safety or the emergency power supply is ORed together with a 12-volt battery. In the event the 12-volt battery dies or goes away, the 12-volt will continue to be supplied by the emergency power supply here. And so it assures a form of redundancy and allows the continuous safe operation of the traction inverter by the user. And so in this case, we're going to be talking more about operating this emergency power supply to the 800-volt bus. And what's important to understand here is that this bus voltage eventually something that could be at a very wide voltage condition. So there will be times wherein, especially when it needs to be maintained and so on, that you have to discharge this to a safe extra low voltage, which is less than 60 volt DC. And so we expect an emergency power supply will be operating as low as 30 volt to whatever the higher bus voltage requirement will be. And so we're talking of very extreme input voltage condition, while at the same time maintaining a good output regulation for the gate driver. Okay. So that's how the emergency power supply works. Now let's talk more about the key component that is going to be used for this emergency power supply. And so what I'm showing here is the application schematic of the InnoSwitch3-AQ. And so the InnoSwitch3-AQ is comes from the InnoSwitch3 family, and what it has is that it has an integrated 750 volt power MOSFET together with a primary controller. And the hidden line here shows this magnetic coupling through the flux link. And then you have a secondary controller here, which is driving the synchronous rectifier MOSFET. Now, this configuration that I'm showing here right now is for a 400 volt bus application, okay? And so this design is actually scalable, and by the use of an external stack FET, which is connected in series with this integrated MOSFET, you could actually scale up and be able to accommodate a design for an 800 volt bus. Okay, so again, this is showing here at the secondary. We continually monitor the output voltage, and the flux here provides the communication control path and a reinforced isolation control path communication between the secondary and the primary. So what is happening at the output, that information is being fed back to the primary controller. Thus, the primary controller can accurately maintain and control the switching of the primary MOSFET in response to what is actually happening at the output. So what this means is that you actually have here is a form of secondary side control or secondary side sensing regulation. And what it does is that it allows the output voltage to be tightly regulated even the load condition changes or the input condition changes. You're always maintained to have a very tight output voltage regulation. Not only that, any transient load changes at the output, since it is continuously being monitored by the secondary controller, that information, you have a high bandwidth form of communication path between the secondary and the primary, and so that allows very fast transient response as well for the Inno3. And again, Inno3 is intended to have no optocoupler design, so you actually have the feedback control loop through the flux link, which is isolated, and so there is no need for an optocoupler, and still you're able to get very good secondary side regulation control. Okay. Now moving on and try to kind of give a bit more background about these flux links. So the flux link technology is a magnetic inductive coupling. So you've got inside the chip are isolated, lead frames that functions like a transformer, and so it provides a way to be able to couple and perform an isolated channel for communication, bidirectional communication between the primary secondary or secondary to primary. Now there's an 11 millimeter spacing between both sides of the switch, allowing a reinforced isolation to be met. There's also 3.3 millimeter spacing between the drain to source for this Inno3. Again, as I mentioned, because no optocoupler is used, this flux link technology magnetic coupling is very fast. It's a high bandwidth application, and so we could respond very fast to different transients situation coming from the output, and so we could tightly regulate always the output even very wide input voltage range. Okay. Now, what's also interesting is that we've gone through and make sure the robustness of the flux link, even in the event of catastrophic failure. So just imagine if you have the Inno3, you have a very high voltage, a fault voltage that is applied across a drain to source beyond its, way beyond its rated capability. And so it generates what we call as catastrophic failure. It's a high energy failure wherein you severely damage the part. And what we want to be assured of is that even in the event that a catastrophic failure happens, we want to make sure that the isolation, the reinforced isolation integrity is still maintained even in the event of such failure happening. So what we did was we tested several parts, about 20 of them, picked them up from the factory, and then we apply catastrophic failure for each one of them. And then after that, we were able to confirm that the isolation is maintained by testing high pot, 4.5 kV for 60 seconds, and of course the trip current is set to 2 milliamps. So all 20 out of the 20 parts tested have their, been catastrophically failed, but all 20 passed the high pot testing, meaning that they all have their reinforced isolation integrity even after the event of a catastrophic failure. So I want to show the test setup that we've used. So we're replicating what similarly would be the situation in an electric vehicle. So we use quite high, about 1000 microfarad of capacitance, and we're able to use a bulk of capacitors here and charge them up higher than the breakdown voltage, and we're using very low inductance IGBT to turn on and off. Okay, so it replicates what a typical catastrophic fault that could possibly happen in electric vehicles. Okay, now let's talk a bit more detail about this 800 volt bus, 800 emergency power supply design. So let's define what the power supply spec is. So this power supply that we're going to share is going to operate a minimum of 30 volt and can go as high as 921 volts. So it's an extremely wide input voltage, and of course the output power varies with the input voltage. So for the nominal bus voltage, we're looking at a 30 watt output power application, and is configured for a 12 volt output. So let's discuss a bit more what the schematic of this power supply would look like. So you have this Inno3 configured in a flyback topology. So you have your input here. The input can be from 30 to 921 volt. And you've got the output here is set to 12 volt output. You've got, this is your secondary side. So this is your secondary transformer winding. You've got synchronous rectification here being controlled by the Inno3 secondary controller. You've got output capacitors here, and this is your feedback resistor network connected to the FB pin of the Inno3. Now looking at the primary side, so you've got your primary winding here, and you could see here also is a transistor, an external transistor Q4, and that is connected in series to the drain to source of the 750 volt integrated MOSFET. So this is Q4 is what we call as the stack FET. Okay, so because it is connected in series, so if you apply 800 volt bus, we could be able to distribute the voltage stress and of course the thermal stress as well between the two power switches. Now, you've also got the usual, RCD clamp, and you've got this auxiliary bias winding as well, providing the bias supply for the controller of the Inno 3. Now, what's interesting to note are, if you would like to come up with a scalable design and say I want to use pretty much the same schematic for, say, for example, a 30 to 550 volt input application, which is a 400 volt bus, I basically depopulate these components here and use a jumper on the board to short the drain to source here, and then you have a design optimized for 30 to 550 volt input. Now, if you want to have operate it at a higher bus voltage, higher than this, 1250 volt. So you've got a 500 volt MOSFET here together with the 750. If you add them together, that gives you the 1250 volt, combined voltage rating of the two. Now, what's interesting is that you could eventually, choose a higher MOSFET rating for the stack FET. So say I want to use it for a higher bus voltage application, then I just basically pick up either a 550 volt or a 650 volt MOSFET, and so you end up with a much more combined higher voltage capability. Okay, so there's a lot of flexibility in the design. Now, as I mentioned, you could come up with different voltage rating as appropriate to your application. So you could optimize it to your spec requirement in terms of the input voltage, and you can also at the same time optimize it. If you don't need a 500 volt, you can try to use for a lower bus voltage and so on, a lower voltage rating based upon your specs. So there's a lot of flexibility about it. Now, VR2, VR3 here sets the clamping voltage, which is the maximum voltage that the drain to source of the Inno 3 will see. And so you could easily set or program the stress distribution between these two power MOSFET. And so it gives you a lot of flexibility, not only from a voltage stress perspective, but from, more importantly, the thermal stress perspective. So since now you have two power switches, and so you could better, more uniformly distribute or spread out the heat dissipated by the power switches, which is very good. So it provides additional benefit from that perspective as well. Okay. Now, let's look at the board implementation of that power supply. So you've got your stack FET here, and this is the Inno 3 here. And so it is a very, there's a lot of opportunities to make it smaller, of course. And, it's simple. It's using, in this case, a multi-layer board. And we're using, again, the copper layer of the board as the heat sink. Okay, so it's a heat sinkless design, so which is pretty neat, low profile and so on. Now, how does the efficiency look like? It's pretty high efficiency even with the addition of the stack FET. So for the 800 volt bus, we're still looking at around 83% efficiency at full load of 30 watts. So it's still way higher than what automotive would see, and so it still offers a relatively high efficiency flyback solution even with the addition of the stack FET. Okay, and again, as I mentioned, you could adjust the selection of the stack FET based on the rating requirement and the input specs that you're trying to achieve. And so it's a very scalable, flexible solution to use, allowing us to reduce our time to market and be able to come up, with solution that could be reused even as the spec evolve and change towards higher bus voltage. So it's a very scalable, upgradable, and flexible design which help us reduce time to market and of course significantly reduce engineering development effort as well. Okay. In terms of output regulation here, it's a big advantage because of that flux link. And so even as your input voltage changes, we are able to maintain plus and minus 3% output regulation as you change from 130 to 921 volt. And even as the load changes from 0 to 100% load. So it's very impressive being able to come up with a very tight regulation even as the input voltage varies. So it's a big advantage from a system design perspective. Okay, so to wrap up, what we've just presented here is the EPS, is the emergency power supply, that is high efficiency using the Inno3 INN3977CQ together with an external stack FET. So you could use it for 800 volt up bus application. There is no optocoupler needed, and we're still able to maintain very tight output regulation, of course, very fast transient response performance. The ISO 26262 is the one drives the need to add an emergency or backup power supply in the traction inverter in order to prevent undefined gate driver condition in the event that you have the 12-volt battery failing or getting disconnected or so on. So, and at the same time, because it's able to operate at a very wide input voltage range, it's safe to be operated eventually by maintenance people. Okay. Again, we have boards available that are able to support an emergency power supply designs with ultra wide input voltage. So we have a DER840Q that is available for 30 to 550 volt. And we also have DER859Q, which is able to do the 30 to 920 volt DC for 800 volt bus. So both boards are available, and the design reports are also in the website. And so please feel free to refer to that if you need more details on the technical implementation. Okay, so that's all for now. And again, thank you for joining me today. I do appreciate it. Okay, bye.